like all good speakers, I've changed my title because the talk has evolved when I've given it some thought over the last few weeks. So I'm going to talk about hazardous elements in both plastic and glass articles for food contact. And I'll talk mainly about the recycling issue, but some other important aspects as well. The outline of my talk, I'll just briefly mention plastic additives. I'll talk about some of the regulations for hazardous chemicals in plastics, in particular European ones. What are the sources of hazardous chemicals in plastics? And some examples of how this translates into food contact plastics. And then I'll finish off by just mentioning a little bit about some findings in glass and put that into context by talking about the shortfalls of some of the regulations that we have. So plastic additives, they've been a sort of mainstay of the plastics industry for several decades, and we have functional additives for all sorts of purposes in plastics. But perhaps the four most important ones for a health concern and an environmental concern are flame retardants, in particular brominated flame retardants, heat stabilizers in PVC, pigments for color, especially historical ones, and plasticizers. And here is a summary of some of the directives, some of the regulations dealing with hazardous chemicals in plastics. And two of the ones that are perhaps important for us are the packaging and packaging waste directive here in red, and one that's been mentioned before, I think, food contact articles. And if we have a look at this list here, we see that two of the chemicals that appear very commonly are cadmium and lead built into these regulations. Also an important component, which I'll mention here, BFRs. Now, I know we've had a definition of BFR before this afternoon, but in this context, it's brominated flame retardants. We have a look at the packaging directive that the limits for cadmium and lead plus chromium and mercury are a total of 100 micrograms per gram or parts per million in any packaging. And food contacts, there are different limits. These are not migratable ones, these are totals. Lead is 2 micrograms per gram, and chromium 6 is 1 microgram per gram. But one other piece of regulation, legislation, which is interesting from our point of view, and you'll see why shortly, is what's called the Restriction of Hazardous Substances Directive. This deals with electronic plastics, and you may be thinking, why is that relevant here? All will become apparent shortly, but the electronic plastics industry and the RoHS directive state that cadmium, lead, chromium, mercury, and brominated flame retardants are restricted in any electronic plastic. A little bit more detail on that then. The RoHS directive came into force in 2006, and basically it states that in any new product, any new electronic or electrical product, the limit values for compliance are bromine as certain flame retardants, 1,000 parts per million, cadmium 100 parts per million, and lead, along with chromium and mercury, 1,000 parts per million. And that applies to any component of electronic equipment. So if you take your laptop, it could be the keyboard, it could be the casing, it could be the hard drive, the motherboard, the wiring. Any part of this has to be compliant with these regulations. So bromine, obviously, as a brominated flame retardant, is a deliberate additive in electronic plastic. It's used because anything electrical needs to have some flame retardancy associated with it. But what about things like lead and cadmium? How do they end up in electronic plastic? Well, this is mainly the recycling process. And when you're recycling electronic equipment, during the separation of materials like metals, plastics, glass, there is scope for cross-contamination, and plastics become contaminated with lead through solder joints, PVC, cadmium can become contaminated in the plastic through semiconductors and pigments and so forth. So electronic plastic is a sort of hodgepodge of all sorts of contaminants, but in particular these three, which can get transferred into or recycled from electronic plastic. Now, this diagram here, we could argue it's a little bit out of date, but it shows the general process. If we have electronic waste, in Europe, let's say, how we deal with this normally is we would bale it and ship it abroad for the components to be separated, including plastics. I've got down China here. China has in fact been taking less and less of our electronic waste, and it's gone off to places like India and Nigeria recently. But there is a question of whether this is legal or not. The Basel Convention states that hazardous waste must not be exported. But the loophole here is that this is going for recycling. So if it's going for recycling, then it's not classified as hazardous. Returning to the plastics, plastics should be separated according to whether they have an excess of flame retardant, lead and cadmium and so forth, or if they're compliant and they have low values, relatively low values, or no detectable values. If plastic contains these chemicals, it should be incinerated and destroyed by a cement kiln, for example. If there are safe levels of these chemicals below the RoHS limits, this plastic can be reused and recycled, and ideally it should be recycled into new electronic goods for export and resale. So we have this sort of circular economy, but getting rid of all the nasties through this process here. But this really is the Achilles heel, this sorting of plastic here. Because if we look in reality, what happens is a lot of the material that is non-compliant, contains high levels of lead, cadmium, flame retardants, is actually fed back into consumer goods rather than being incinerated. So we end up with consumer products being exported or imported back from recycled electronic waste, which is non-compliant, and that enters its own circular economy. So we're sort of introducing these chemicals into consumer products through this Achilles heel, if you like, here. And you can understand why this is an issue, because when you look at some of the working practices in separating materials out in some countries, then we see they're very crude, and there's no way that people in some of these places have any access to any resources, facilities, motivation, or the technology to sort plastics according to whether they're compliant or not. So that's where the whole system in effect breaks down. So the main consequence is that we are actually importing hazardous chemicals back into consumer goods. And the interesting thing is that these are mainly black goods, certainly dark colors. The reason for this is that if you're aware of the plastic resin codes, to sort plastics at a recycling center normally involves an infrared instrument. And infrared is not very good at picking out black plastic. Black plastic absorbs infrared radiation. So a lot of black plastic actually goes to waste. We think it's being recycled, but it actually goes to waste, which has been there's been a lot of publicity about this, certainly in the UK over recent years. And the supermarkets have been under pressure in many countries for reducing the amount of black plastic because it is effectively wasted. They choose it because it's aesthetically appealing and it conceals certain imperfections in food like meat. But black is obviously a very, well, I'd say from a manufacturer's or a retailer's point of view, it's a very nice color. So we can't recycle black plastic. Where do we get our black plastic from that is recycled? Well, we get it from electronic waste. And I don't know about you, but I'm sat here in front of a black keyboard, a black mouse, black iPod, headphones, black laptop. Black is a very popular color for electronic plastic. and therefore it's a convenient and a cheap source of gaining recycled black plastic. And when you look at food contact articles, here's a few examples of things that are commonly black and made out of black plastic. So coffee pods, coffee plungers, straws, cocktail sticks, draining boards, ice cream cartons, cutlery, very commonly made out of black plastic, which there is evidence for it being recycled from electronic waste. And we've done some simple tests using portable XRF. We've looked at plastics. We can't determine the type of flame retardant, but we do have other indicators that give us a pretty good idea of what types of flame retardants we have from bromine, and certainly very good for cadmium and lead. So here's a selection. These have all been recycled from electronic waste. These are polyethylene, polypropylene, polystyrene, and ABS plastics, consumer goods. And you'll see amongst this, there are several food contact articles. Going through some measurements, and these are the food contact goods, 6 of them all together. We see that lead is detectable with some quite high values in some cases, up to about 50 parts per million. Cadmium, similar story in those products. We find it in most of them, and we find a similar range in concentrations. Bromine, again, we find bromine in these products, but quite disturbingly, perhaps, we find levels which are up to 6,000 parts per million in this cocktail stirrer, and well over 1,000 in this black fork. So what about the compliance with regulations? If we take the 2 examples before, the food packaging and food contact regulations, we find that there are certainly non-compliances because the lead and cadmium is greater than 100 parts per million in 2 cases, and lead is greater than 2 in at least 5 of those 6 products. But the interesting thing is that 2 of those products are potentially non-compliant with respect to the RoHS directive. In other words, 2 of those products, including those cocktail stirrers, are perhaps compliant with respect to food safety, but are non-compliant with respect to electrical safety. In other words, you wouldn't be allowed to use those plastics in a laptop or a phone, but you can use them, according to the regulations here, in food contact articles, which sounds really bizarre. Just to add another complexity, PET, which is used to store and contain a lot of food in many products and many circumstances, does not seem to contain lead, cadmium, or bromine. The reason for this is PET is not a particularly common plastic in electronics. So PET thankfully escapes this sort of cycle and this problem. And just one second example to finish off with. I thought I talk about plastic a lot, but glass seems to get away with a lot, I think, and there are some problems with the glass industry and food contact articles. I'm sure you're all familiar with these. These are alcoholic beverages which are painted with or embossed with a logo, okay, on the outside. Okay, you may recognize these. They occur on other food contact products as well, glass as well. The problem is that this decoration is highly toxic. The cadmium level in this example, this is a bottle of red wine, after the contents had been consumed, obviously. Cadmium concentration, nearly 20,000 parts per million in the red here. And the reason cadmium is commonly used is that it's a heat-resistant pigment. It can withstand temperatures going through the glazing, for example. And on top of all of this, throughout this whole area here, we have a layer of lead oxide, nearly 50,000 parts per million, which way exceed any guidelines, any regulations that we have. The response from the glass industry is that this is part of the glass. So in other words, if you divided these concentrations by the weight of glass, you get a much lower value overall. And the fact is that the bottles would be compliant, or the product. But I've always questioned whether this is a component of the glass. And I think a key indicator is whether this will come off or not. You know, is it part of the glass, or will it dislodge or deteriorate? Well, if we go to, I've got an example in a moment. Here's just to show you some of the lead and cadmium values for plastic. Certainly, we're looking at 100 or 2 microgram per gram. So these values are really excessive. But this was a product that we bought from a supermarket here in the UK a few weeks ago. And we stored this in the fridge, our fridge, and some of the soy sauce leaked out of the top, just a small amount. And you can see that the cadmium pigment is actually coming off. And in fact, when you put your fingers on this, or you put a damp cloth across it, the yellow cadmium ink comes off extremely easily. So I would argue that any glaze and any pigmentation on top of a glass bottle is not part of the glass, and therefore this sort of product is completely non-compliant. So it does pose a significant and a direct human health risk if this stuff can come off on your hand. And it also contaminates the glass cullet. If you keep decorating glass like this and it's recycled, then the cadmium and lead levels in the glass itself will actually just continue to go up and up and up. So it does have environmental and human health risks. So to finish off, recycled electronic plastic appears to be one of the main sources of hazardous contaminants in food contact materials. And it's largely limited to black plastics, but not PET. And this is because black plastic is difficult to recycle from an infrared point of view, and the fact that many electronic items or plastics are indeed black. These are unintentionally added, we could argue, but certainly with respect to glass decoration, cadmium and lead are deliberately added to the glass containers for decor. And if there was anyone from the glass industry there in the audience, I'd like to know why cadmium and lead are deliberately added in this way. Why aren't safer alternatives being used? Is it traditional? Is it to cut costs? I just don't know, but I just find it quite alarming, really. And there are regulations really needed to close loopholes in terms of hazardous plastic exportation, which is one of the issues we have. We should be perhaps looking at our electronic stream more closely here before we export it and just sort of ignore it. We should be recycling materials or thinking of regulations that cover one material has a certain function recycled into a product with a different function. Should we be thinking about regulations that go across the recycling spectrum, say from electronic to food contact? Should we be using the same sort of regulations there? And should we be thinking about components of articles that pose a hazard rather than the whole product? I'm talking really about something like a decorated glass bottle here. Okay, thank you for your attention. That's me done. And I hope I haven't opened up too many cans of worms.